Many students think that the resistor networks are really difficult, so we do not have to learn them. Theories behind the system of resistors, so resistor networks, are really important throughout the current electricity, especially on Kirchhoff laws as well as magnetic fields and electronics. So if you think that these theories don't just 1 mark, you are misunderstood. So this video is about the simplification of electric resistor networks. So it's Gayan Fernando here, and Gayan Fernando is an educational channel. So if you haven't subscribed me yet, please consider subscribing. And today's video is the 5th part of the video series of current electricity. And as I said before, we are going to learn about some important theories behind system of resistors. First theory is goes like this: the length of a conducting wire can reduce to 0 by mind. To do so, there should not be any resistance in the wire. This theory says if any wire do not have any resistance, by default we do not consider the resistance of a conducting wire. If especially in the question they have given the resistance of per unit length of the wire is this much, then there exists a resistance, and this theory does not valid for them. If there is no any statements like those, so then by default there do not exist any resistance on the wire. So then we can reduce its length to 0 by our minds. For an example, this is an example resistors example which can do by that. These wires, we can reduce those lengths to 0. If we do so, this point will come to this, and this point will come to this point. So the network will look like this: 3 wires, then 3 ohm, then 3 ohm, and finally 3 ohm. So this is point A, and this will be point B. And again, these are 3 wires. If we reduce these wires lengths to 0, then the point A will go to this point. So the resistor series system will look like this: 3 ohm, 3 ohm, and 3 ohm. Point A is this, point B is this. This is a simple parallel system. So the resultant 3, 3, 3, the resultant resistance will be 3 divided by 3, that is 1 ohm. So that's it. So let's go to theory number 2, that goes like this: any closed loop that does not contain electrical cells can be eliminated from the circuit. That says any closed loop that does not contain electrical cells, simply the batteries, can be eliminated. So this is an example for that kind of system. We know that the current always passes from high electric potential to low electric potential, simply high voltage to low voltage. So if we assume that there exists a current in this loop which does not contain any electric cells, the current, since current passes in this direction, so the voltage will reduce again, and voltage will reduce again, and again come to that point. So it can be happen there's a contradiction in there. As we said, it starts from some value, then the value is reduced and come again to that value. That can't be happen. So that implies that the current will be 0 in this branch, in this loop. So this loop will be eliminated, and the resulting simplified network will be look like this. Only 3 resistors, 4 ohms, 2 ohms, 2 ohms, A and B. We know that 2 and 2 equals 4, that 4 and this 4 equals 2. So that resultant equivalent resistance will be 2 ohm. Let's move on to the theory number 3. It says that the points having same electric potentials can be connected or disconnected as you wish. If you know that some 2 or more points have same electric potential, you know that. If you know that, then you can either connect them, or if they are already connected, you can either disconnect them as you wish. It's your preference. So this is a theory that helps to some other theories comes back. This, for example, the theory 4 says, if the circuit is symmetrical around the perpendicular bisector of the line drawn from A to B, A and B are the electrical systems starting and ending points, then the electrical potential of every point along the perpendicular bisector is the same. So you can use theorem 3. It says that if AB's perpendicular bisector is a symmetrical axis, then all the points of that perpendicular bisector has the same electrical potential. So you can use theorem number 3. For an example, let's take this. Here, this point should be B. Here, this line, that is the perpendicular bisector of A and B, is a symmetrical line, symmetrical axis for this system. So we can we know that all the points on this perpendicular bisector is equal. So consider this node right here. If I enlarge that node, it will look like this, and there is a connect between these two. So I can enlarge furthermore like this. So the perpendicular bisector goes like this, and this in this wire, in this connection, the electric potentials are the same. So I can disconnect them by using theorem 3. So if I disconnect them, the system will look like this: 3 ohms, 4 ohms, 3. This is point A, this is point B. The values are 3, 4, 3, 2, 2, and 4, 4. So we disconnect this and these points. So now we can simplify. This 2 and 2 equals 4. That 4 and this 4 equals 2. That 2 plus this 3 and this 3 equals 8. So we have 8 ohms from above, and this 4 and this 4 equals 8. So 8 from below, point A and B. So we know 8 and 8. So 8 and 8, two identical resistors in parallel. So the resultant will be resultant resistance will be 8 divided by 2, that is 4 ohms. So that's the resultant equivalent resistance for that system. And we are moving on to now theory number 4. If the circuit is symmetrical around AB line, we discard on the fourth. If the system is symmetrical along the perpendicular bisect of AB. Now, if the it is symmetrical around AB, then the circuit can be folded on AB. In this case, three things happen. One, every respective resistance except lies on the AB becomes half of the value. Secondly, resistance on AB will not be changed. Thirdly, resistors cut the line AB will be eliminated. So, for an example, take this. For this system, this line, this AB line is a symmetrical axis. You can see. So, I can fold that. If I fold that, only the below part or above part should be drawn. So, the resulting system will be like this. This is the point A, this is the point B. Now, take these resistors. This 2, 4 and this 2. These resistors lies externally to the line AB. So, this will be half. So, the values will be 1 ohm, 2 ohm and 1 ohm. This 4 resistor is a special one. It lies along the AB, so it will not be changed. So its value will be remain unchanged by 4 ohms. And this is a very special resistor. This 4 ohms, it cuts the line AB. If a resistor cut the line AB, it will be eliminated. So it is looped off. So that resistor will not remain anymore. So this is the simplified system. If I simplify them, we know 1 plus 1 is 2. 2 plus this 2 equals again 1 ohms parallel due to parallelity, and that one and this one will be 2. So the system will be 4 ohms by above and 2 ohms by below. So 4, 3, A and B. So the resulting value will be 4 by 2. 4 plus 2 will be 8 divided by 6, that is 4 divided by 3 ohm. So this is the equivalent resistor. Finally, we are moving on to theory number 6. If you can move from a point to another point, at least one path only on a wire. So you should not meet any capacitors, any resistors, any electric cells. Then the resistance between these 2 points is 0. For an example, take this. In this system, take these 2 points, this point and point B. I can move from this point to point B only on this wire. I have a path. That path doesn't contain any capacitors, any resistors, any electrical cells, just only a electric wire. So that the resistor between those points is 0. So that means the resistor between these 2 points will be 0. So only the resistor remains is this 2 ohms. So the system will look like this. Just 2 ohms, A and B. So the equivalent resistance will be just R equivalent will be 2 ohms. Simple as that. So with that theory, this video comes to an end. If you really enjoy this video, please hit the like button and please consider subscribing. Hit the bell icon right next to the subscribe button so you'll get notified whenever I upload a new video. Please share the video with others so they can learn something too. So I hope to catch you guys in the next 6th part of the current electricity. So until then, goodbye.